Hello everyone, welcome to the course of Digital Logic Design. In today's class, we are going to learn the topic Boolean Algebra and with respect to logic gates. So first of all, what is a Boolean Algebra? It is a set of rules, laws and theorems by which all the logical operations can be mathematically expressed. Okay, so these Boolean Algebra can be mathematically expressed with the help of a logic gates. Now, what are these logic gates? Logic gates are small electronic circuits designed using electronic components like diodes, transistors, resistors, and so many small electronic components. So these logic gates are further classified into various types, and we are going to see what are these types of logic gates. So coming to the logic gates, these are majorly classified into basic logic gates, universal logic gates, and derived logic gates. So coming to the basic logic gates, we will be mostly seeing three types of basic logic gates, that is AND gate, OR gate, NOT gate. And coming to the universal logic gate, we find NOR gate and NAND gate. And coming to the derived logic gates, that is XOR and XNOR gates. Okay, these falls under derived logic gates. Okay, so these each and every logic gate will be having its own symbol and its truth table. Okay, so we are going to see the overview of each and every logic gates truth table and its diagram as well. Let's see the first basic gate, that is AND gate. So this AND gate will be having two inputs and one output. So let's see the diagram. So this is the symbol of an AND gate where it will be having two inputs and one output, and the output is derived based on the two inputs, that is A into B. So based on this, we have a truth table where the inputs A and B will be having a combination of 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So if you do the AND operation with respect to the two inputs A and B, for 0, 0, the AND operation will be 0, 0, 1, it will be 0, 1, 0, it will be again 0, and for 1, 1, it will be 1. Okay. So this is the truth table for an AND gate. Let's see the next logic gate. So coming to the next logic gate, we are going to see the OR gate, where again OR gate will be having similarly like an AND gate, it also will have two inputs and one output. So this is an OR gate symbol where it will be having two inputs, let's say A and B, and one output, where the output of an OR gate will be sum of these two inputs like A plus B. So coming to the truth table, so we will be taking the combinations of inputs like 0, 0, 0, 1, 1, 0, 1, 1. Okay. So an OR result for two inputs 0, 0 will be 0, 0, 1 will be 1, 1, 0 will be 1, and again 1, 1 will also will be 1. So this is the truth table with respect to the OR gate. Coming to the next logic gate, that is NOT gate. Okay. NOT can be also considered as an complement or an inverted gate also, where it will be having one input and one output. Okay. So let's see the symbol. So this is the symbol. So it will be having, as I said, it will be having only one input and one output, where the output will be complement or inverted of the input. Like if the input is 0, then the output will be 1. If the input is 1, then the output will be 0. Okay, it will be reverse. Coming to the next logic gates, universal. Let's see a NOR gate. So NOR gate is a combination of OR gate plus NOT gate. Okay, so let's see the truth table of NOR gate. So we have again the combinations 0, 0, 0, 1, 1, 0, 1, 1, like two inputs and one output will be there. So for 0, 0, the output for an OR gate will be 1. 0, 1, the output will be 0. For 1, 0, the output will be again 0. And for 1, 1, the output will be 0. So this is a symbol of an OR gate where you will be having two inputs and one output. Now let's see the another universal logic gate. So this is a NAND gate. Okay. So in most of the mathematical expressions for solving that, we'll be using these kind of NAND gates, where NAND gate is a combination of AND gate plus NOT gate. Okay. So this is the symbol of an AND gate, where it will be having two inputs and one output. And coming to the truth table, again, we are taking the combinations of 0, 0, 0, 1, 1, 0, 1, 1. Okay. So the 0, 0 of an AND gate will be giving us 1, and the inputs 0, 1 will be giving us 1. Inputs 1, 0 will be giving us again 1, and the inputs 1, 1 will be giving us 0. Okay. So this is the truth table of an NAND gate. And let's see the remaining two logic gates, that is XOR and XNOR gates. Okay. So this is the XOR gate, where you will be having two inputs and again one output. And the logic gate or the truth table of this particular XOR gate will be, for 0, 0, the XOR operation will be 0. 0, 1, the XOR operation will be 1. 1, 0, the XOR operation will be 1. And for 1, 1, the XOR operation will be 0. Okay. And coming to the last truth table, it is XNOR gate. So obviously, XNOR gate will be a combination of XOR gate plus NOT gate. Okay. So it will be reverse of XOR. So this is the XNOR gate, where you will be having two inputs and one output, and this is how the symbol looks. And coming to the truth table, for the combinations 0 and 0, the output will be 1. For the combinations 0 and 1, the output will be 0. For the combinations 1 and 0, the output will be 0. And for the inputs 1 and 1, the output will be 1. Okay, this is how an XNOR gate truth table will be. Okay, so all these logic gates are useful for the mathematical representation, or they are included in the circuitry of the Boolean expressions or Boolean functions, or majorly they are applied to the digital electronics.